we are done with the regression where the target or labels are continuous values. Here it's more discrete with different categories where you have to predict the classes given an input. Okay, and in specific, we'll be looking at logistic regression and k nearest neighbors. Okay, so first, classification. Is it a supervised or unsupervised paradigm? What do we do? Is it supervised learning or unsupervised learning? You have your features, you have your labels. Okay, anyone? So if you have both your features and your label, it's called supervised learning. Okay. You have a set of feature values which can be both numerical or categorical, but the output value is categorical. Okay. Output label is also categorical. And the model is the method you use to predict labels from feature values. Okay. Example, let's say you are doing shopping. Okay. And you are building an ML model to predict whether, given a particular age, gender, and income, whether you will buy this product or not. This is a classifier, a classification example. So, so what do you do is supervised learning. Mm. So you learn a function f, you learn this line, okay, to predict y the labels given an input x. Regression will be like this, where you will be uh, here you have something called you see some sort of a separating line, right? So points to this side are, let's say, buyers, and points to this side to the right are not buyers. Okay. Here you predict points on each line, on this line. Okay, that is what is regression. Another classification example where you look at clothing items is the fashion MNIST data set, okay? Where you look at clothing items and let's say this is a bag, this is a sneaker. You can classify it accordingly, given just the picture to your machine learning model and so on. Other examples would be credit card fraud detection. The features can be the user, the location, the age, and whether based on it, you predict where is a credit card fraud has happened or not in this case. So I have given two other examples. Okay, can you all just tell me what can be the features and what can be the labels for these two cases? What can be the features? What can be the labels you need? Use case. Okay, so given an email, you're predicting whether it's spam or not. What can be the features? You have the email text with you. What can be the features? Okay, in the case of medical diagnosis, you can look at chest X-rays, okay, where you look for certain bright spots, the chest X-rays at certain location, and check whether it, whether there is any disease or not. That is medical diagnosis. Email spam detection. Given email text, you can search for certain words such as give your phone number or like card information, OTP, or such, and then predict the email as spam or not. The presence or absence of those words. That is one feature. I mean, you can use different features like how much text is there and so on. But yeah, uh, moving on, there are uh, so regression and classification are somewhat similar except for the label value that is being predicted. Okay, but there are different algorithms like k nearest neighbors, logistic regression, naive Bayes classifiers, SVMs, neural networks, and so on. Yeah, there are a lot of classification algorithms very similar to what we saw in regression also. Okay, looking at KNNs. Okay, how does it work? First, you are given a pair of data items. Okay, so this is one pair, this is another pair. What KNN will do, okay, will calculate the distance between these two data points. If, let's say, this is a new data point that we have, okay, this is an existing data point where you predict credit card fraud has already happened. Okay, you compute the distance between this and this. If it is closer, okay, then it's more probable that uh, this person has also gone through credit card fraud. Okay, that's the main idea here. Another thing, same case, you have uh, this. You have two persons. One is a buyer, one is a non-buyer. This is how your data set will look like. Okay, so to classify a newer item, okay, you find the k closest items to the new item and assign the most frequent label. Okay, let's say I have another new item to classify. Where do we assign this? We have to check whether it's more closer to the non-buyer or whether it's close to the buyer. Based on that, you predict the label for this person. Okay, there is let's say a very simple numerical example. Okay, you have city temperatures of India and Germany. Okay, the features are longitude and latitude. You need to calculate the distance. Okay, these are some labels: cool, warm, and cold. Okay, now I have another city, Velur. Okay, and I that comes with this longitude and latitude. How do I classify this city? What do we do? Can anyone do this calculation? Okay, so you have something like this. You have to do this operation. Okay, you have to do this for each pair. So Velur Chennai, Velur Madurai, and Velur Frankfurt, and see where the distance is lowest among these three. Can anyone calculate and tell me fast? Or you can just look at it and tell me. Like, so this is obviously close to, if you just look at it, Madurai, and you can classify Velur as being warm. Right? So this is the final summary, okay? You have to define the distance function. Once that is defined, uh, so you have initial data like this. class 0, class 1. You have a new point. Okay. You find the k closest neighbors. If k is 3, so these are my three closest neighbors. Okay. These are my three closest neighbors. So what label should I get here? Majority. Is it class A or class B for this point? Class A or class B? What class is majorly represented when k is equal to 3?
Class B.
Yes. So this is how it works, general. Okay. This is what KNN is. Uh, yeah. Then we'll be looking at the implementation also. Moving on to logistic regression. Okay. This is also a supervised learning method. It can be used for both classification as well as regression if your regression label is between 0 and 1. And you have to predict the categorical dependent variable with the help of all these independent variables. And the output of logistic regression is always between 0 and 1. Okay. Mm, what it does is it will give you the probability of uh, whatever labels that you have, okay, whether it's fraud or not. Ultimately, it's what you learn, linear regression with the sigmoid activation at the end. So this is the sigmoid activation. I mean, you don't need to go into the details of this. Uh, so logistic regression is just combining linear regression with sigmoid. We'll look at it in the tutorial. Okay? But how do we actually evaluate whether your model that you have built is actually good or not? So there are all these evaluation metrics that you have. Okay. For regression, there are two major metrics called coefficient of determination R square and mean square error. For the classification case, you have F1 score, you have accuracy, receiver operator characteristics, AUC is area under the curve. There is precision, there is recall. There are a lot of metrics to determine whether your model is actually good or not. Ultimately, if you want to evaluate your classifier, you have to get this table called the confusion matrix. Okay. So you have actual labels with you, right? The positive and negative. You also have your predictions from your models. You just calculate how much, if your actual label is positive and your predicted, let's say and your predicted label is negative, okay, then your model has actually given you a false negative. When your actual label is negative and your predicted one is positive, then your model has given you a false positive. Okay? So this is called type 1 error, type 2 error. Again, no need to go into the details, but this is what a confusion matrix looks like. So your ideal model, okay, what should be the values for false positive and false negative? What should be the values for false positives and false negatives? Your model is 100% accurate, predicting everything properly. This thing. Okay. It should be zero, right? You want all your predictions to be either true negative or true positive. If it's zero, then you have your ideal classifier. Okay. Uh, then there is precision and recall. Okay. So higher precision means that your classifier is able to give more relevant results. Okay. And recall more relevant results than the irrelevant ones. And recall is a measure of quantity that will give you how much, uh, how many relevant items are retrieved among. Okay. So if you look at this figure, you have true positives, false negatives, and true negatives. Okay. Let's say for the precision metrics, you are asking the question, how many retrieved items are relevant? Okay. But in the case of recall, it's like how many relevant items are being retrieved. So can you just tell me the formula for precision recall just by this color coding? So it will be the number of true positives divided by true positives plus false positives. Okay. So it's essentially looking at, and I mean, if you have higher precision, meaning all the items that are retrieved are relevant. Okay. In the case of recall, it's true positives by true positives plus false negatives. There you have a measure of quantity. Okay, that says like how many relevant items are retrieved. Okay. Moving on to the ROC, AUC, ROC curve. So, okay, let me ask you this question. Instead, I mean, let's say your classifier algorithm gives you probabilities. Okay. The value that you get is zero point 0.4. Would you classify it as a negative example or positive example? Your output from your classifier is zero point 0.4. You set some threshold, like let's say if it's below zero point 0.5, I'll classify it as a negative example. If it's above zero point 0.5, I'll classify it as a positive example. Okay. So in this case, you are putting an arbitrary threshold called zero point 0.5. Okay. Let's say your threshold is zero point 0.3, then zero point 0.4 will be classified as a positive example. So you have to check different thresholds. Okay. 0.5, 1, different thresholds and see how many true positive or false positives you are getting. Okay. If your model is able to predict the true positives in a perfect manner, I mean, what I mean, without I would say without caring about the threshold, then you have the perfect classifier. Your curve will be like this. A random classifier will have the ROC AUC curve as this one. Okay. As the curve keeps moving towards the y-axis, you will get a better perfect classifier. And how do you evaluate your models? They are same, like you split your data set into train set, test set. Okay. You do whatever model development on your train set, then get your predictions on test set. Test set, you don't use it to train your model. Okay. You only get predictions from the test set. Then there is another way called k-fold, where you split it into equal chunks. Let's say you have 7 chunks of data here. You pass 6 for training, keep 1 for validation, and keep changing this one again and again. Like in the first round, this will become the test set. These will become the train. In the next round, this will become the test, and the rest will become train, and so on. So there are different ways of doing your splitting. Why do we need to split it into train and test? Why do we need a train and test split? Ultimately, if you deploy your model in the real world, okay, you keep getting newer and newer samples that might not uh, be from the same distribution as your train set. Okay. So what you do here is you just test your model, like without giving any additional data other than the training set. If some other new data point comes in, how my model is performing. That is what you're checking. Okay. Uh, to summarize for today, I've used 2 algorithms, K and logistic regression. I've also introduced metrics for evaluation and how to do evaluation with cross validation here. Okay. So, I mean, any doubts? If there are no doubts, I'll start the tutorial also right now. Python notebook. Anything I need to explain again, I can do it. Or if you didn't understand anything, I can start from the first also. Just let me know something. Perfect. Sorry, I just muted. Yeah. So you have different distribution of classes here mentioned in
இந்த
this.
பொசிஷன்ல பார்த்தா யாராவது தப்பா தான் நடப்பாங்க.
Okay.
இந்த பொசிஷன்ல பார்த்தா யார் நம்ம அதுவும் அவன் ஷர்ட்ல இல்ல அவளோட.
I think someone's mic is on. Okay. So I'm splitting the data set. Okay. I'll drop the species column, assign it as Y, and the rest will be my X being my feature matrix, Y will be my label vector. Okay. I'm using some standardization. This is something you have to do with your data. I'm also using a label encoder where, see, directly I can't just give iris setosa, iris virginica as input to my model. Okay. You should convert it into categorical values. So here, what I'm doing is, wait. So I'm assigning it these values, okay, 0, 1, and 2. 0 for setosa, 1 for versicolor, and 2 for virginica. You have to assign some class values, okay? Because your models directly can't take string as input. It always deals with numbers. You have to remember that. So that's why I'm using this label encoder class to convert it from the string to class values. I'm doing the train test split here. Hmm, This is so yeah, this is my confusion matrix that I have here. Okay, these are my predicted, these are my actual. So what do you? So let me ask you this question: where how many iris versicolor classes are being predicted properly by the model? How many? Based on this table, just let me know. Just look at this table and let me know how many iris versicolor data points are being predicted correctly as iris versicolor. So it's 5, right? Because the actual values are predicted values. So you have to check the diagonal elements in the table. Okay. This is not your perfect model, but it's somewhat good. Then there are different classification metrics. These are the formulas to calculate all these metrics that you have. We'll start with logistic regression. Okay. You use the logistic regression class in scikit-learn. You already split your data set, right, into train and test. You fit only on train, okay, not on text, not on test. get predictions on test, and get the accuracy. Okay, so there is fit, predict, score. Three different things. Okay. Okay, this is my, I've got all my predictions. I have my labels, I have my predictions here. I'm generating my result. What do you think about this? Is this good? Is this model good? Is this model good? It is good because it's almost perfect. Instead of 10, 10, 10, I mean, just one sample is being predicted wrong. Yeah, my accuracy is like 0.97 and F1 score is 1, the recall is 1. So my model is very good. Okay. We'll look at time base later. Let's look at KNN. You just have to, same thing that you have to follow. Okay. You Instead of logistic regression, you use K neighbors classifier, do fit, predict, score. My accuracy is around 96%. But there is one thing that we can change the K neighbors classifier. What is that value that we can change? I mentioned K, right? K is something that we need to change for different data sets. This is what I would say is called hyperparameter tuning, where you have to, for each data set that you have with you, you have to try to change the K value. Here I'm defining a range from 1 to 20. So for each value in this one, let's say I keep increasing K from 1 to 20, getting my accuracy score. And if you see it, this is my plot that I have here. Okay. So what should be my, yeah, see, this is my plot. So what should be my K value here that I have to select to make sure that my model is the best? What should be the value of K or neighbors?
12.
Yes, because that's the one with the highest score. So for each data set, you have to do this. Okay, try different values. So each model has its own set of hyperparameters. For K nearest neighbors, it's only K. Okay. But as you go on, when we go through multiple algorithms in this course, you will get to know that each model has its own set of hyperparameters where you have to tune them. Tune meaning try different combinations and see that which particular set gives you the best possible score. Okay. Uh, okay, this is, yeah. And since okay, moving on to multi-class classification. Okay, let me do this. And you have three different classes. Okay. If you just have two different species for you to classify, it's called a binary classification. If it's more than two, let's say 0, 1, and 2, it's called multi-class classification. Okay. So ordinary classification approaches binary classification approaches might not work out of the box for multi-class classification. You have to make some changes. So that is what I'm doing here. Okay. What I've done is something called one-hot encoding. Okay. See, instead of 0, 1, and 2, I've transformed my data set like this. So if it's 0, 0, 1, it corresponds to the class 2. If it's 0, 1, 0, It's class 1. So what will be the value for class 0?
One zero zero.
Yeah. So this is what I would call as one hot encoding. Okay. You always have to do this for multi-class classification problems. Uh, Here, it will automatically handle it by default for you. But if you want to visualize the AUC curves and everything, see, Setosa is transformed as 100, ID is 0, and let's see the RC curves. So this is there are different approaches called one versus one versus rest, and something else. You don't have to go into the details, but just look at this curve. Is my model better than the random model? Yes or no? These ROC curves you can only generate for binary classes, okay? So what I've done is I've considered Setosa as one class, combined Virginica and Versicolor as another class. That's why it's written one versus rest. So is my model better? Is my model good? What do you think? This is the performance of the model that I've developed. That is logistic regression. This is by randomly I'm predicting. So let's say I have like 100 samples. Randomly I'm putting 0, 1, 0, 1, 0, 0 for all those predictions. If I do it randomly, I'll get this curve. If I train a model and do the predictions, I'm getting this curve. So is it better than the random model? As I told you, when your model, the RSC curves for for the model that you have built is very closer to this side, your model is obviously better. As long as it's not below this diagonal line, your model performance is good. So the value is 0.89, better than 0.5. So the model you have developed is quite good. And whatever newer features that you get, you can predict it properly. Let's say I have okay. So randomly, I'm giving four different values for four features. Okay, it is predicted the class as one. One corresponds to, I think, Warsaw. I'm not sure, but yeah. So this is how machine learning works. You train your model. Training meaning you do fit. Okay, then you can do predictions for whatever new data points that you have, and then check whether it matches with the original labels or not. So this is how typically the classification pipeline is implemented. Okay. Any doubts? Okay. Don't see anything in the chat also. Okay. Please stop sharing. Let me just share this. Yeah, I'll share this in the drive folder later along with data set. But yeah, any doubts? If there are no doubts, we can in the class here. Okay then. Thank you all for attending. See you all on Tuesday.